Hello everyone and welcome to the 8th episode of CPP Next. In this episode we will talk about CRTP, or Curious Recurrent Template Pattern. During my last visit to CPPCon, I heard many people were confused about what CRTP is and what is it used for. So in this episode I want to showcase and explain why do we need it and how to use it correctly. Let's start diving in. So what is exactly CRTP? In simple terms, it's a way to create a compile-time polymorphism. But why? For that, we need to understand how dynamic or runtime polymorphism work. And therefore, I already presented these two classes that have dynamic polymorphism, because class A is our base class and class B is inheriting from class A, and that means we have a dynamic polymorphism. So let's dive in and try to understand what happens under the hood. Let's start by looking what will happen if we want to create an object of type A. This is our base class, and that means we're creating an object of type A. But because we used virtual keyword, the compiler will add a virtual pointer to the object. It is hidden from us, but it is there because we have used virtual. And it will also create a virtual table for object of type A. And that means when we are calling it, we have this connection. The virtual pointer will point at virtual table A, and from virtual table A, foo and bar functions will point back to the A class implementation of foo and bar, because this object is of type A. Now let's look what will happen if we want to create an object of type B. In this case, we still have an object of type A, and it resides inside the object of type B, because when we are creating B, we are creating its inherit object as well, and it is A. We have the virtual table for A, we have object B that only implements foo, and we have the virtual table for objects of type B. The connection is like this. Virtual pointer will now point to the virtual table of B, because we know at compile time that the object is of type B and not of type A, and that means the compiler will set the pointer to point to the virtual table of B. Foo function will point to the object B itself, because the implementation of foo is implemented in B. Bar is not implemented in B, and that means it will point to the function that is implemented in A class. And that means when we will call it, we will call bar from A. Now let's look what actually happens if we want to call a function from B object called foo. Of course, we have our objects that we already created, and we have the virtual tables for them. Now, when we want to call this function from object B, we will access the virtual pointer. The virtual pointer will point us to vtable B, because we knew in compile time, and the compiler set virtual table B to the virtual pointer. And from there, we will know that foo is actually was implemented in objects of type B, and it will point us to the code area where type B was implemented. And if needed, we know that this is always available to us, and if we have members, we can actually access them from this. This is called dynamic dispatch, and sometimes it's less performant. Notice that I use sometimes because modern processors are so good with virtualization optimization that for some cases there is no hit in performance, or it even performs better. But this is for another episode. So for now, that we understand the dynamic dispatch, we can understand that CRTP can remove that by providing static polymorphism. Let's understand how CRTP works from this example. Now, let's try to understand what happens here. So we always have to start with a templated base class that is templated on some type. In this case, this class will be called same, and it will only have one function, the equals operator, that receives two types from the templated types. That means that we don't need to cast. And the templated type has to have the less operator inside it. Afterwards, and here is the CRTP itself, we're creating a new struct or class called dumbbell. And it's publicly inheriting from same, and we are templating it on itself. So this is CRTP. We are templating the base class on the class that we are creating right now. That means the base class will know which type we're using, and that means we don't need a dispatch. In this class we have a weight, and we have the operator less than that we need for same. Less than is of course very simple. It checks if the weight is less than the weight that we received from the other. Then we can look at the main. Inside the main we are creating two dumbbells, D1 and D2, with weight equals 10 and 20, and we will return 0 if D1 equals D2, and return 1 if D1 is not equal D2. And notice here we have static dispatch, because dumbbell is publicly inheriting from same, and we are not using virtual at all. No virtual tables here. Same knows exactly which templated type it's templated on, and it's dumbbell. That means it knows which class it uses, and it uses the correct operator less than for the operator equals. And because operator equals was implemented in same, we can use it on dumbbells. And this is CRTP for you. And this is kind of cool for something that has been with us since C++98. It's a very important pattern to understand because it is actually used in standard library until this day. To showcase it, one of the very important implementations in the standard library we got with C++11 is enable shared from this. And enable shared from this is an example for CRTP. Basically, you can see here that is used exactly as CRTP is used. We are creating a class, and then we are publicly inheriting enable shell from this and providing ourselves to the enable shell from this class. I just wanted to show you that it's still used until today, and it's important to understand this pattern, but enable shell from this is important enough for me to create an episode about it by its own. So thank you for watching. Hopefully you understand now what CRTP does, and as always, like and subscribe, and see you in the next episodes.